Funding for this program is provided by Annenberg CPB to advance excellent teaching.
Kepler's second law, an imaginary line from the sun to our planet, sweeps out equal areas in equal times. This law of equal areas also applies to the vortices of hurricanes, firestorms, even bathtubs. And at the center of this swirling motion is the law of the conservation of angular momentum.
In the 16th and 17th centuries, that brilliant reawakening known as the Renaissance came to an end. And Europe turned its attention to a lively debate on the finer points of Christian theology. That period, known as the Reformation and Counter-Reformation, culminated in the bloody 30 Years' War. During that time, three giants walked the earth. In the long run of history, they would turn out to be more important than all of the bishops and kings put together. Their names were Galileo Galilei, Johannes Kepler, and Tycho Brahe. Galileo, of course, we've already met. I'll tell you more about Brahe later. The time now has come to speak of Johannes Kepler. Kepler certainly didn't seem like a giant. In fact, he was small, frail, nearsighted. He suffered from fevers and stomach disorders. He was subject to cycles of deep depression and bubbling, soaring elation. The elation was usually associated with some scientific discovery that he had made or thought he had made. He was also rigorously honest. For example, he described his own mother as being garrulous and bad-tempered, and his first wife as being fat, confused, and simple-minded. And he wrote about his science in the same way. He wrote about how he had done it, about his failures, about his feelings while he was doing it, all of that in addition to what it was he had actually done. That's not at all like the way scientific papers are written today, in which each one seems to be a flawless triumph of inexorable logic, which of course is never true. He was also a mystic. In fact, he was a professional astrologer. In those days, mathematicians had to cast horoscopes in order to make ends meet. Kepler thought that all astrologers were charlatans and frauds, that is, all other astrologers other than himself. He cast his own horoscope, deciding that he had been conceived at 4:07 a.m. on the 16th of May in 1571. Well, he may have been conceived that night, and he may not have been. It was his parents' wedding night, and he was born 7 months later. He was an authentic genius. For example, in the course of resolving a dispute about the shape of wine barrels, he very nearly invented the integral calculus. He also discovered many laws. 3 of them turned out to be correct, and it's for those that we remember him.
One of Johannes Kepler's 3 laws, the second, reveals a most beguiling and pervasive principle of nature. A principle that explains the shape of galaxies and fury of hurricanes, and even those comparatively calm whirlpools in the family bath. In the end, Kepler's second law was seen as a simple consequence of the law of conservation of angular momentum. But in the beginning, his idea was viewed as a way around a body of Greek knowledge cast in stone, an outrage against the accepted anatomy of the universe. Kepler stood up to the classical astronomers, and in doing so, turned his back on almost 2,000 years of collective wisdom. Astronomy, even before medicine, was practiced as the first physical science. In ancient China and Greece, in Babylon, in Alexandria around the birth of Christ, in Copan, sacred scientific center of the Mayans, within the wisdom of the Caliphate of Baghdad, in the Moorish Alhambra, where mathematics and art combined to make grand designs, wherever people relied on the cycles of nature, and that's wherever crops were planted, people relied on astronomers to point the way, foretold by the stars. The more astronomers knew about the heavens, the more effective they were on Earth. So they attempted to reproduce heaven on Earth, a model of the universe that duplicated the star-filled configuration they'd observed night after night for ages. This was no easy task, not even for the best minds of the Golden Age. The Greeks created all sorts of original schemes until about 350 BC. That's when a philosopher named Aristotle came along to share a few thoughts about the nature of everything under and including the sun. One of Aristotle's ideas held firmly that the earth is the center of the universe. He also convincingly argued that all heavenly bodies move in perfect uniform circles. They really don't. Therefore, to draw the planetary motions along Aristotelian lines, astronomers had to recreate a cosmos of complicated circles, moving around on top of other complicated circles. This roundabout system of epicycles was bizarre, complex to the point of being almost incomprehensible. But it saved the appearances, which was scientific double talk to justify fitting round pegs into square holes. And besides that, in many practical ways, it actually worked. For example, it more or less predicted the positions of stars and planets. It aided navigation, and perhaps most important, it helped astronomers to cast royal horoscopes, which was a vital component in their job security. Indeed, the Aristotelian view, with the Earth at the center of a universe in which all motion was uniformly circular, satisfied almost everyone. Almost everyone except Nikolai Copernicus, who around 1500 wrote an intellectual tornado of a book, The Revolution of Heavenly Orbs. Within these pages were ideas powerful enough to uproot and send the Earth hurtling through space, tossing aside the very foundation of physical science in the process. In one otherwise innocent chapter, Copernicus recreated the universe. He put the sun, not the Earth, at its center. And he put the Earth, as if it were a mere planet, in orbit around the sun. The Copernican universe was an idea as revolutionary as any before or since. In fact, from Copernicus onward, the word revolution has meant radical change. Yet even while attempting to overthrow the Aristotelian stronghold, Copernicus retained that ingrained practice of the astronomer's trade to save the appearances. All the planets did orbit the sun, he ventured, and not in perfect circles at uniform rates. However, in order to save appearances, he ventured no further. Copernicus concluded his book by spinning the age-old yarn of epicycles. So, in the end, the Copernican system was not only bizarre like the one it was supposed to replace, its revolution was almost hidden behind a smokescreen of astronomical complexity. Nonetheless, such ideas gave off sparks that fired the imagination of Johannes Kepler. He knew Copernicus had undermined the structure of the first great dictum of antiquity. And since the Earth was no longer the stationary center of the universe, Kepler was free to go around uniform circular motion. But what could take its place? Answering that question took the better and the worst part of Kepler's life. A journey with calculations that stretched from one end of Europe to the other. Finding the answer took everything he had and anything else he could borrow from his contemporaries. His was a hard road, but at its end the man called the wandering mathematician could describe the motions of the planets. Going further than Copernicus, Johannes Kepler had found the 3 laws of planetary motion. Kepler's first law gave the orbits of the planets a new, non-circular shape and put the sun a little off the center of things. Now, in the course of its travels, a planet is sometimes closer to the sun and sometimes farther away. According to Kepler's second law, the closer it got to the sun, the faster it moved, and the farther away the planet got, the slower it moved. His third law said that the larger a planet's orbit, the longer it took to go around. Kepler's 3 laws describe the heavens with mathematical precision. At the same time, his principles are at work closer to home. Kepler's second law explains why even the most playful water spirals down the drain in a very strict manner. Going round and round, circling faster and faster, the water finally ruptures and forms a hole in the center, a whirlpool scientists call the vortex. Not every vortex remains so calm or within human reach. An upwelling of air, moving at first in gentle circles, can twist itself into an awesome vortex, the hurricane. As an astronomer of the 1600s, Kepler was concerned with the weather, but his search for the answer to why the planets move as they do led him above the Earth's atmosphere. He never determined why planets move faster when they're closer to the sun. It would take Newton to do that. But Kepler did discover how much faster they approached it. As a planet moves around the sun, the vector from sun to planet sweeps out equal areas in equal times. When the planet's far from the sun, moving slowly, it sweeps out an area in a certain time. When it's closer to the sun, moving faster, it sweeps out the same area in the same amount of time. In 2 sweeping gestures, that's Kepler's second law.
The vector sweeps out an area in the form of a triangle. The area of the parallelogram formed by 2 vectors is the cross product. The area of the triangle is just half that. Turn this into a derivative, and the result is the rate of change of the area vector. dA dt is equal to 1/2 r cross v, a constant, the same in all parts of the planet's orbit.
Kepler's law of equal areas doesn't apply only to orbiting planets. Here, each drop will obey the same law. The water seems calm, still, motionless. But due to the Earth's rotation, among other reasons, water in any container constantly circulates. And sometimes, circulating water has an increasingly amazing effect. At first, it drains nice and smoothly. But flowing inward, the water begins to circle around the drain, and just like Kepler's planets, it sweeps out equal areas in equal times. At the same time, but unlike the planets, the water moves in smaller and smaller circles, faster and faster until its vortex develops, and the whirlpool remains the center of attention until all the water's gone. Once the vortex gets going, it's hard to stop. Circulating or rotating objects, a planet, water, even an ice skater, all obey the same basic law. It's not the law of equal areas, which is a related but incidental consequence of a deeper law of nature. It's the law of the conservation of angular momentum. What is angular momentum, and how does it work? The conservation of ordinary momentum comes directly from Newton's law. Force equals rate of change of momentum. If there's no force, the momentum doesn't change. It's constant. In other words, the momentum is conserved. But there's a strange twist when the momentum is angular. Even if there is a force applied to a body, something may still be zero. And something is equal to zero. Not the force, but the twist. To put it mathematically, R cross F equals 0. Obviously, not all forces behave that way. For example, to open a valve, or to get a wheel rolling, twist is just what's needed. However, for a planet in orbit, or for water flowing around and down a drain, even for a hurricane, there's no such twisting force. In fact, gravity and fluid pressure, the main forces at work on planets and vortices, can't twist about the center of the motion. Why? Because in these cases, R cross F equals 0. When force is 0, momentum is conserved. When R cross F is 0, something else is conserved. So what is R cross F the derivative of?
The answer is found by differentiating R cross V. Use the product rule. dr dt is V, and V cross V is 0. So the derivative of R cross V is R cross A. Now multiply by the mass. L is m times R cross V. If R cross F is 0, the quantity L is conserved. L is called the angular momentum. R cross F, the twisting force, is called torque. For example, a planet in orbit has no torque. It conserves angular momentum. That's why Kepler's second law is true.
According to the law of inertia, a body moving in a straight line will continue at constant speed unless a force is applied to it. In a similar way, a spinning body rotates in the same direction unless a twist or torque is applied. This is the essence of the law of conservation of angular momentum.
The angular momentum, L, is a vector following the right-hand rule. For circular motion, when V and R are perpendicular, the size of L is mRV. To keep L constant, if the circle gets smaller, the speed must get bigger. The same basic rule explains Kepler's second law. In an elliptical orbit, a planet must move faster when it's closer to the sun, and slower when it's farther away.
The same idea applies to a spinning ice skater. With no torque applied when she pulls in her arms, her whole body spins faster to conserve angular momentum. Of course, to a considerable degree, warm water differs from ice, but the physics is much the same. Water that's not in a solid state lacks enough viscosity to apply much torque. Its main force is directed toward the hole to replace the draining water. Far from the center, water circulates in great lazy circles. But as it's forced toward the center, its speed increases until, like a tornado, it ruptures into a vortex. A tornado, often called a twister for good reason, is the same phenomenon as the whirlpool in a bathtub, only upside down. This vortex starts when calm air at the center moves upward, forcing circulating air inward to replace it. Sometimes the upwelling occurs because of fire. When a vortex develops, it's called a firestorm, literally a hurricane of fire. It wasn't Mrs. O'Leary's cow that caused Chicago's razing devastation in 1871. It was the vortex of her firestorm. And as victims under fire learned during the Second World War, once firestorms get started, they're held to stop. Seemingly, they last forever. The red spot of Jupiter is an enormous hurricane, and that one's raged at least since 1610. Galileo was the first to view it, as well as Jupiter's moons, orbiting in a plane. Likewise, the rings of Saturn are satellites on a plane surrounding a central body. The structure of the entire solar system is built along the same lines. Beyond that, many galaxies share the basic shape of a flat disk around a globular center. In the structure of the universe, why is this disk shape so pervasive? Probably because of the conservation of angular momentum. Picture a galaxy starting out as an enormous spherical glob, a massive slow rotation of matter, of protostars and debris and cosmic dust. Picture each bit of matter attracted by the gravity of all the matter inside, and piece by piece, condensing toward a point in the center. As the particles move inward, they pick up speed, whipping around faster and faster rather than falling to the center. They're in orbit, and they continue in orbit forever. That's the way angular momentum helps to design the universe.
In 1562, there was a major conjunction of the superior planets. This event was watched with bated breath by a world steeped in astrology. It turned out that the old astronomical tables were a few days off in predicting when the event would occur, and the new Copernican tables were even worse. All of this had a stunning effect on a young Danish aristocrat. His name was Tycho Brahe. And he realized that the reason that the predictions were poor in both systems was that the necessary, precise, and continuous observations had never been made. He decided to become an astronomer himself. He persuaded King Frederick to give him an island called Haveen off the coast of Denmark, where he built a palatial observatory and the finest astronomical instruments that had ever been constructed. He not only made the necessary observations, he also created his own universe called the Tychonic universe. You remember, that in the Aristotelian universe, the Earth was at the center and the other bodies rotated around the Earth on crystal spheres. The Copernican universe changed all that by putting the sun at the center and making the Earth one of the planets. But it was still basically a universe that rotated on crystal spheres. In the Tychonic universe, the Earth was at the center, just as in the Aristotelian world. And the sun rotated around the Earth, but all of the other planets rotated around the sun. To us, looking back on those times, the Tychonic system seems like a compromise between the Aristotelian world and the new Copernican world. But in those days, it was a radical innovation, because by having the planets rotate around the sun and the sun around the Earth, he smashed the crystal spheres of both older systems. Of course, Tycho believed passionately in his own system. In fact, he considered it his most important accomplishment. But we know, looking back in history, that his real most important accomplishment were those careful, systematic observations of the skies. Before Tycho, the positions of the heavenly bodies were known with an uncertainty of 10 minutes of arc. That's about 1/6 of a degree. You can get an idea of how big 1 degree is by holding up one finger at arm's length like that. And you can easily imagine primitive observations with an uncertainty of about 1/6 that. By the time Tycho was finished, the uncertainties in the positions of the heavenly bodies had been reduced to 2 minutes of arc. And it was from that small but crucial improvement that the rest of our story flows. And we'll go on with that story next time.
The angular momentum of an object is defined as the cross product of the radius from a specified point and its momentum. A force that applies a twist is called a torque and is equal to the cross product of the radius and force, R cross F. The torque is equal to the rate of change of angular momentum. When no torques act on an object, the object's angular momentum is conserved.
It's 26 weeks. It's emotions, right? 26 weeks.
Marvin is my friend.
Well, it saves the way of excellent.
Yeah, unfortunately.
It's not good to be out early. Sure it is. You come back late.